Here are two boxes, each starting with particles tightly packed into one corner, 2 on the left, 800 on the right. Both expand to fill their boxes, then move around freely. First, we pause right after the expansion and play the film backward. With 2 particles, everything still looks natural, as if time doesn't care which way it's going. But with 800 particles, we clearly notice the video is going backward. There's a break of time symmetry. Next, we let the video run forward again through the equilibrium. Then reverse it. This time, both boxes behave identically. We can't tell if the video is going forward or backward. This intriguing asymmetry, where direction matters at first but then seems to vanish, and only manifests itself for systems with many particles, is at the heart of a concept called entropy, a profoundly important but often misunderstood quantity in physics. The first chapter is going to be about information theory. First, we will define the initial problem we need to solve. Then, we will define what information really means in the information theory framework. After that, we will see a simple coin problem, which will allow us to introduce entropy. And finally, we will talk about the maximum entropy principle, effectively solving the initial problem. Imagine rolling a dice, but unlike a regular dice, you don't know how likely each face is. We first define a probability vector P, which captures the probability distribution of the dice, each coordinate corresponding to the probability of one outcome. These probabilities must satisfy certain rules. For example, probabilities have to add up to 1 because the probabilities are normalized. Given this normalization constraint, you could imagine many ways this distribution might look. Perhaps all faces are equally likely, giving a uniform distribution. Or maybe the dice is rigged, making one face nearly certain and the rest almost impossible, which seems heavily biased toward one outcome, given how little information we know. But let's add a twist. Suppose we know one more detail. The expected value of a roll is exactly 4.5. This extra piece of information limits our possibilities dramatically. Some outcomes, like the uniform distribution, now become impossible, while others become more likely. We could associate faces 4 and 5 with 50% probability each, which, intuitively, seems heavily biased toward these two outcomes. Or choose a distribution closer to the uniform one that still satisfies the new constraint. Yet, even with these constraints, there remains uncertainty on the probability distribution that we should pick. Our challenge is the following. What is the least biased probability distribution we can assign, given everything we know and nothing more? This question, subtle but fundamental, leads us directly to the framework of information theory. Imagine a mathematical construct, a black box. We feed this box 2 key inputs, constraints about our probabilities, and a probability vector. What it provides as an output is the least biased probability distribution in the form of another vector. But here is the key insight. These constraints are more than just restrictions. They're a form of information. They represent what we know about a system. We could imagine that this mathematical construct represents the missing information of the system for a given probability distribution. To solve our initial puzzle, we maximize this missing information relative to the constraints. In doing so, we embrace our ignorance fully, acknowledging every possibility allowed by our limited knowledge. Edwin James Thompson describes it very elegantly. To quote him, "This sounds very much like defining a variational problem. The information available defines constraints, fixing some properties of the initial probability distribution, but not all of them. The ambiguity remaining is to be resolved by the policy of honesty, frankly acknowledging the full extent of our ignorance by taking into account all possibilities allowed by our knowledge." To identify this mathematical construct, we must define the information content of a probabilistic event. We will call it I, and it's a function that takes the probability of an event, which is 0, 1 with 0 excluded, and returns a real positive value. This information content must satisfy 3 conditions to be consistent with what we expect to be information. First of all, the information of a certain event, which has probability 1, must be 0, as something guaranteed to happen doesn't bring any information. Secondly, the information content should be a decreasing function of the probabilities. If an event A has a lower probability than an event B, then this event A has a higher information content than the event B. This is because we can also see the information content as how surprising an event is. The less likely an event is to happen, the more surprising it is when it does happen. Finally, if two events are independent, then the total information content is the sum of the information content of each individual event. This third requirement is by far the most important. If C is the joint event of A and B, then the probability of C happening is the probability of A times the probability of B knowing A. And if A and B are independent, then the probability of B knowing A is just equal to the probability of B. This means that the information content must be a function that satisfies the following functional equation: f of x times y equal f of x plus f of y. This means that the information content of the joint event must be equal to the information of the first event plus the information of the second event knowing the first event. The only set of functions which satisfy this functional equation are the logarithm functions. We can choose any basis that we want for the logarithm. For example, in information theory, we will often take b equal 2 to get the binary logarithm, but we can also choose any other base like b equals e in statistical mechanics to get the natural log. The minus sign ensures the second condition, that the function is indeed a decreasing function of the probabilities. We can also remove the negative sign by taking 1 over the probability in the logarithm. Here is a plot of the information content in an arbitrary base for the logarithm. As we can see, the information goes to 0 as the probability approaches 1. On the other hand, the information diverges as the event approaches 0. I have said earlier that the information content can also be seen as the amount of surprisal. To illustrate this, I will provide the following example. Let's say that you throw a dice that lands on face number 2, and 3 of your friends have to guess what the result is going to be. If your first friend tells you that the result is even, then you would be a bit surprised. They indeed have a correct information on the result, but they could have been lucky. There is a 50% chance that the result was going to be even. Your second friend tells you that the result is lower or equal to 2. Then you're a bit more surprised. Indeed, there's only a 1 in 3 probability that the result was going to be lower or equal to 2. So compared to your previous friend, it is much less likely that they have guessed that randomly. Perhaps they have found a way to cheat. Finally, your last friend tells you that the result is 2. Then you're extremely surprised. They have the correct answer, which you're not expecting since there's only a 1 in 6 probability to guess the correct answer randomly. Let's introduce a simple problem. We have 4 labeled boxes, 1, 2, 3, and 4, with a single coin hidden randomly inside one of them. Initially, the coin ends up in box number 2. We have to retrieve the coin by asking binary questions, which are questions that can be answered by yes or no. The goal is to solve the problem by asking the least amount of binary questions on average. Our first approach is naive. We check each box one by one. Checking box 1 first, there's a 1 in 4 chance of success, but this attempt fails. Next, we check box 2, where the probability of success has now become 1 in 3 due to the conditional probabilities after eliminating box 1. This time we succeed, retrieving our coin effectively in just 2 steps. Now let's move the coin to box 4 and repeat this same basic process. We start by checking box 1, failure. Next, box 2, again, no coin. Checking box 3 is another miss, but this time we retrieve the coin because it's automatically in box number 4 since we have eliminated all the other boxes. It took us 3 steps to solve the problem. On average, if we follow this simple method of sequentially checking boxes, it will take us about 2.25 steps, with a considerable variation, which is represented by the sigma, of around 0.83. In practical terms, while sometimes we might get lucky and find the coin immediately, About half the time, it will require the maximum 3 steps. To address this inefficiency, let's bring information theory into the picture. Information theory provides us with a powerful framework to optimize a strategy. Each yes or no question provides us with a measurable amount of information depending on the result. Let's illustrate this. If we check box 2 without prior knowledge and fail, we gain a relatively small amount of information. We do not know the state of boxes 1, 3, and 4. However, if we succeed by checking box 4, the information gained is significantly greater. We also know that all the other boxes are empty. Our goal is therefore to ask binary questions that maximize the information gained. Let's define a new quantity h, which we will call entropy. Entropy is defined as the expected value of the information content of a probabilistic system, calculated as the negative sum of the probability times the log of the probability for each possible event. For example, let's briefly compute the entropy for a single binary question, checking if the coin is in a specific box, with no prior knowledge. I recall the probability vector on screen. You can pause the video and try to compute the entropy by yourself. With the given probability vector, the entropy calculation results in approximately 0.81 bits if we choose the log to be in base 2. This means that without any prior knowledge, if we check the content of one of the boxes, we will on average get 0.81 bits of information. The advantage of binary questions is that the probability of success is p and the probability of failure is 1 minus p due to normalization. We can therefore express entropy as just a single parameter p and plot it in 2D. Although the expression of entropy is somewhat complicated, the curve is quite simple. It is a bell curve with a maximum at probability 1/2. Before we keep going, let's try to make sense of what we're seeing here. In the limit where the probability of success goes to 0, the entropy we get is 0. This totally makes sense because in that scenario, we already know the answer of the binary question before asking it. We get no information. The reverse scenario is also true, where if the probability of failure goes to 0, then the probability of success goes to 1, and the answer to the binary question is already known before asking it. The entropy of the binary question is maximal when the probability of success is 1/2, and therefore the probability of failure is also equal to 1/2. Therefore, if we build a binary question with probability 1/2, the information content we will get for the outcome is going to be the log of 2, no matter if it's a success or a failure. And in log base 2, the logarithm of 2 is equal to 1 bit, which is greater than the value we previously computed. Let's apply this optimal questioning strategy to our previous scenario, with the coin in box 4. Our first question should evenly split our possibilities. The question could be, is the coin in box 1 or 2? Here, the answer is going to be no, so we immediately eliminate half the options, which are boxes 1 and 2. Then, we have to ask a second binary question, which again, should evenly split our possibilities. The binary question could be, is the coin in box number 3? Here, the answer is no again, but we have located the coin now. No matter where the coin is located, and no matter the answer of the binary question, which evenly splits our possibilities, we will pinpoint the exact location of the coin in exactly 2 steps, completely eliminating any uncertainty. This optimal method, in contrast to our naive sequential checking, consistently retrieves the coin in exactly 2 steps, with 0 variation. We might not have the chance for immediate success, but consistently, over multiple trials, we will outperform the naive strategy on average. So far, we've talked about the entropy of a binary question. But our coin in boxes puzzle isn't just that, it's an entire system. So what is the total entropy of that system? If the system is made of n boxes, all having the same probability of holding the coin, then the probability vector is uniform. Given these 2 expressions, you can try to pause the video and find out the entropy of the system. Because all events have the same probability, the sum simplifies and everything collapses to log n. However, we could also have noticed that every single event here has the same probability and therefore the same information content. because entropy is the expected value of the information content, the entropy here is just the information content of an event of probability 1 over n. Now let's plot the entropy of the system based on the amount of boxes. We realize that when the amount of boxes is squared, the entropy only doubles. This is a phenomenon that has an intuitive geometric explanation. If we have 4 boxes like previously, we can rearrange the boxes to form a square. The total entropy of the system is log 4, which in base 2 gives an entropy of 2 bits. We solve the problem with the optimal method by asking 2 binary questions, which evenly split the possibilities. Now let's square the system. We now have 16 boxes. Here the total entropy is log of 16, which is equal to 4 bits as the entropy has now doubled. To see why the entropy has only doubled, we can first create 4 clusters of boxes, represented in yellow. Then we can decompose the main problem into 2 sub-problems. The first one is to locate in which cluster the coin is located, and then in which box of the cluster the coin is. Because we have 4 clusters which have the same probability of holding the coin, the first sub-step is exactly symmetric to the one where we had to find the coin in one of the 4 boxes. We therefore solve this problem the exact same way, taking only 2 binary questions. Then we have 4 boxes left in the cluster, and the problem is again exactly the same as previously, where we solve it by asking 2 binary questions. The amount of optimal binary questions we had to ask has doubled. Thus, for a uniform system where every outcome has the same probability, entropy in base 2 is the exact count of optimal binary questions one needs to ask to uncover the full information of a system. Entropy can therefore be seen as our missing information on a system. Finally, I want to show a last example where boxes don't have the same probability of holding the coin. Given the following system, each box is associated with the probability it has of holding the coin. You can try to compute the entropy yourself by pausing the video in log base 2, where log 2 equals to 1. We show that the entropy of the system is equal to 1.5 bits. The entropy is no longer an integer. The first binary question we will always ask is whether or not the coin is in the box with probability 1/2. If the answer is yes, we have retrieved the coin in exactly 1 step. If the answer is no, it means that the coin is in one of the 2 remaining boxes. Then we can ask whether or not the coin is in one of the 2 boxes left, and no matter the answer, we have retrieved the full information of the system in 2 steps. We see that therefore, if we play a lot of times, it will take us on average 1.5 optimal binary questions to locate the coin. There is no longer an exact amount of binary questions you need to ask to solve the problem. Now let's go back to the initial problem where we had to associate the most fair probability distribution to a dice. Here is our histogram of faces, and now in yellow we see the information content associated with each outcome. As these probabilities drift, the amount of information they carry shifts too. But what we really care about is entropy, the total missing information of the whole distribution. So let's swap the information content of each outcome by its contribution to the total entropy. Now we want to choose the probability distribution that maximizes this total entropy while still satisfying any constraints we have. To do that, we introduce a Lagrangian on screen. H is our entropy, and lambda1 is what we call a Lagrange multiplier. G is a function that enters a constraint on the probability distribution when set to 0, which in our case is just the normalization of probabilities. We could add more Lagrange multipliers, each multiplied by another function that enforces a constraint on the probability distribution, but here we will just use the normalization constraint. To find a probability distribution that maximizes entropy, we need to find the probability distribution which cancels out the gradient of the Lagrangian. This condition gives us the following system. We can isolate pi in the first equation of the system, and then plug the normalization constraint, which is the second equation of the system. In doing so, we find the value of the Lagrange multiplier. We can substitute its value in the first equation of the system to find the value that pi must take. we find that the probability that the dice ends up on any of the faces is 1 in 6. In other words, this means that the least biased probability distribution, if we have no information on the system other than the normalization of probabilities, is uniform. Intuitively, this totally makes sense. We have no information on the dice. Giving a higher probability to one of the outcome compared to another would be biased. Now, suppose we add a second constraint on the probability distribution. Like in the introduction, the expected value of a roll is exactly 4.5. In that case, we would introduce a second Lagrange multiplier. In this case, the algebra gets pretty heavy, and I will not display it here. But the result shown here is clear. Higher faces earn higher probability, while lower faces dip. Yet none of them drop to 0. Maximum entropy relative to this new constraint still finds the most uniform distribution compatible with our new constraint. This method, known as the maximum entropy principle, is the only logically consistent way to infer probabilities from partial information, as Edwin Thompson Janes wrote in 1957. In making inferences on the basis of partial information, we must use that probability distribution which has the maximum entropy given what is known. By maximizing entropy, which is the missing information of the system, the best distribution is simply the one that faithfully encodes exactly and only the knowledge we possess. In the next chapter, we will see how this principle is at the heart of the fundamental postulate of statistical physics. In this second chapter, we will see how to use statistics to describe physical systems. First, we will define the notion of statistical ensembles. Then, we will see how to proceed when we want to use a quantum mechanical description of the system. And then we will see how it can be done using classical mechanics. We live in an atomic age. We understand that all matter is made of particles, and that a gas is nothing more than the chaotic motion of countless molecules. But centuries ago, before atoms were widely accepted, thermodynamics described a gas as a continuous fluid, describing it with macroscopic physical quantities like temperature and pressure. In this chapter, we'll build a bridge between that hidden microscopic world of atoms and the simple thermodynamic variables we measure in the lab. The use of statistics to solve the dynamic of a problem doesn't seem very intuitive, but there are three main problems that make more usual approaches impossible. The first one is that there is no analytical solution for the motion of three or more bodies in interaction. The second problem we face is the size of the data. For instance, if we try to store the three components of position and velocity on 64-bit values for 10 to the power 23 particles, which by the way corresponds to 2 grams of carbon, it would require a storage 20 times larger than the entire internet. Finally, the dynamic of a system composed of many particles is chaotic. This means that we would need a near infinite precision for our initial condition, which is not possible. This is why our last resort is to use statistics. To solve our problem using statistics, we first need to introduce the notion of statistical ensembles. In this video, we will only talk about the microcanonical ensemble. It's sometimes called the NVE ensemble because its number of particles, its volume, and its energy are fixed quantities. The microcanonical ensemble therefore represents isolated systems, systems that cannot interact with the outside world, and which are extremely idealized because these systems do not really exist in the real world. The last thing is that we have to modelize physics inside this microcanonical ensemble. We choose our physical model by setting the relation energy must satisfy. Usually it will take the form of a sum of the kinetic and potential energy of each particle, plus the sum of the interaction energy between each particle. In more physical terms, we have defined a Hamiltonian. But to keep things simple, we will just call it the equation that energy must satisfy. As we can see, the variable of this equation are the position and momentum of the particles. The solution to this equation is not unique. There are multiple combinations of momentum and positions which satisfy it. The microcanonical statistical ensemble is therefore the collection of the solutions to this equation. To find how many solutions our energy equation has, there are two different frameworks we should consider: quantum and classical mechanics. We will first start with the quantum case. Let's suppose our isolated system is a crystal. This crystal is made of periodically arranged atoms. But these atoms are not idle. They are oscillating around their equilibrium position, which we can modelize by a 3D harmonic oscillator. However, we also know that the particles are not point-like. If we want a description that works at all energies, we will have to use a quantum mechanical description of the 3D oscillator. Solving the Schrödinger's equation for a one-dimensional oscillator, we showed that the energy levels are quantized. The energy can only take specific values, n being a natural number. We can therefore represent our oscillator as a box, and the value n as the amount of quanta of energy, or quanta of excitation, our oscillator has. If we consider a system to be made of n independent oscillators and m quanta of energy, the total energy can be written as follows. Here I have chosen n oscillators to keep things simple, but if we really wanted to model our previous crystal, we would need to replace n by 3n, because each atom can oscillate in the 3 directions of space and is therefore composed of 3 independent oscillators. We can distribute the quanta of energy among all the oscillators the way we want. The energy equation will still be satisfied. Each of these arrangements is called a microstate, which we will denote by a small omega, the larger omega being the total amount of microstates. As we have seen in the introduction, it is impossible to solve the problem exactly. And even experimentally in a lab, if we took a crystal, it would be impossible to measure the degree of excitation of each atom in the 3 directions of space. But this problem is oddly similar to the coin in the box problem we've treated in chapter 1, except here there are multiple coins, which are just the quanta of energy. We can try to characterize how much information we're missing from the system. We can therefore write the total entropy of the system. But a problem remains. What is the probability that the system is in a given microstate? We have to remember that we are in the microcanonical ensemble, where the amount of particles and the energy is fixed. Therefore, 2 constraints we have here is on the amount of oscillators and on the total energy of the system. These 2 constraints just tell us the domain in which we should count our microstate. In other words, it just associates probability 0 to microstates that have a different energy or amount of oscillators compared to the constraints. This means that every single microstate that meets the requirements must have the same probability of happening. We must have a uniform distribution. This means that if large omega is the total amount of microstates which satisfy the constraints, the probability of a given microstate that also satisfy the constraint is just 1 over omega. The entropy is therefore just the log of the total amount of microstates. This result may seem weird because in most statistical physics textbooks, we often see that the entropy, which is actually denoted S, is equal to Kb, which is the Boltzmann constant, times the log of omega. I will explain it in more details in chapter 3, but it really comes down to how we've defined our unit system in thermodynamics, which was made before statistical physics. To find how many microstates our system has, we have to redefine the problem to turn it into a combinatory problem. To do so, we use a balls and bars representation of our system. Each quanta of energy is represented by a red ball, and each oscillator is represented by the separation between the yellow bars. The oscillators are between each separation, so if we have n oscillators, we have n-1 separations. For example, in this configuration, going from the left, the first oscillator would have 6 quanta, the second would have none, the third one would have 1, the fourth one would have 8, and the last one would have 1. There are many configurations that we can have. By changing the bar locations, we change how many quantas the oscillators have. This problem is easily solved. We have n plus m-1 slots. Keep in mind that the -1 comes from the fact that we have n-1 separations, and we have to place m quanta of energy on these n plus m-1 slots, and then the rest of the slots will be filled by the bars. We can use the binomial coefficient to immediately find out the solution, and we can replace it in the entropy formula. Now, we will use these results in chapter 3 to understand why entropy always increases. But first, we will see how to compute the amount of microstates in classical mechanics. In classical mechanics, it is possible to describe the motion of a body with an infinitely accurate position and momentum. The solutions for the energy equation are therefore continuous. The energy levels are not quantized like in quantum mechanics. We can represent the energy equation solution on the phase space. The ellipse represents all the possible momentum and position that solve the equation. Keep in mind that here we have represented the system as a one-dimensional harmonic oscillator, which has two degrees of freedom, the momentum px and the position x. This is why we can plot it in 2D. But if we had a three-dimensional harmonic oscillator, we would need a six-dimensional phase space, which I cannot represent. And if we had n particle, each being a 3D oscillator, we would have a 6 n-dimensional phase space. So the ellipse that we see here that solved the equation would actually become a hypersurface. Intuitively, we could try to compute this hypersurface size to get the amount of microstates, but there's a problem. What is the size of a single microstate on that hypersurface? The problem now is that we need to define the size of a microstate in classical physics, because this ellipse, or more generally the hypersurface, is made of an infinite amount of points because it is continuous. Ideally, we would like to find a nice correspondence between classical and quantum mechanics. So whenever we take the high energy limit for the amount of microstates in quantum mechanics, we find the amount of microstates in the classical case. The Heisenberg's uncertainty principle stipulates that we cannot measure simultaneously the momentum and position of a particle with infinite precision. Intuitively, we should divide the phase space in cells that have the size of the Planck constant h. There is a formal mathematical proof for this, which I will not display in the video. The second problem that we face is that the energy is not continuous. Therefore, there is a near infinite chance that the energy that we have used here is not allowed by quantum mechanics, and so the amount of microstates would be zero. To make it consistent with quantum mechanics, we will therefore compute the amount of microstates that we have within this small shell. In doing so, we are sure that there will be some energy levels allowed by quantum mechanics that exist. However, computing the amount of microstates within a shell is sometimes complicated. Since we are interested in the logarithm of the microstates because of entropy, we will show that we can simplify the problem. If we notify the amount of microstates of energy below E, then the amount of microstates within the shell is given by the amount of microstates of energy below E plus delta E minus the amount of microstates of energy E. Because phi is just the hypervolume, it should scale as e power f, f being the dimension of the phase space, which means that f is just the amount of parameters that we have in our energy equation. Therefore, the number of microstates in the shell should scale like this. Now, we can use a trick with the exponential of the log to make the log of 1 plus delta E over E appear. Because delta E over E is small, we can make a Taylor's expansion, which leads us to getting the following result. We can therefore rewrite how the amount of microstates in the shell should scale, and since we're interested in entropy, we just take the log and get the following result. If we look at the first term and the second equation, we realize that the first term is just the log of the amount of microstates of energy below E, which scales linearly with f, which is directly proportional to the amount of particles in the system. However, in the second term, we get the exponential of f times delta E over E. In the thermodynamics limit, where the amount of particle goes to infinity, f also goes to infinity. Therefore, the logarithm would simplify to f times delta E over E, which is much smaller than f times ln E. What we can conclude from this is that the log of the microstates in the outer shell is similar to the log of the microstates in the inner volume. Geometrically, it means that the log of the amount of cells in the blue part is similar to the log of the amount of cells in the purple part. Here, this doesn't look really true because we're only in 2D. This is really a consequence of very high dimensional objects for which the volume is mostly located near the surface. Now that we have seen how to compute the amount of microstates in classical mechanics, let's do a small example. To change from the previous example, we will see a perfect gas. The energy of this gas is given by the sum of the kinetic energy of each particle. This is one of the simplest equations we can get for energy. We have to compute the amount of microstates of energy lower than E. First, we have to divide the hypervolume by h power 3n. This is the volume of our elementary cell. The reason for the power 3n is the following. In the previous example, we were only dividing by h because we had a one-dimensional single particle. But here we have n particles that can move in the three directions of space, so our elementary cells are just small hypercubes. Then to compute the hypervolume, we write the following integral that we can separate in two parts. This is because the energy doesn't depend on the positions here. We can therefore directly integrate on the volume for each particle, which yields v power n. Each momentum vector p has three components, x, y, and z. This is why we can rewrite dp1, dp2 to dpn as d3np, which is a simplified notation. We can also rearrange the bone of the integral and realize that we have to compute the volume of a hypersphere of squared radius 2me. The hypervolume of the hypersphere has already been computed by our mathematician friends. We just plug it into the expression. But we need to be careful about one last thing. The particles are indistinguishable because they're all the same. For example, as the video is running, if I inverted the position and velocity of two particles, you would not be able to notice it. To solve this problem, we need to divide our result by n factorial, which is just the amount of possible permutations. We are interested in the log of the microstates, and in the thermodynamics limit, the amount of particle goes to infinity. This means that n factorial and 3n over 2 factorial is extremely large. We can therefore use the following Stirling approximation, and now you can pause the video and try to compute the entropy by yourself. We find the following result, which is also known as the Sackur-Tetrode equation. We also realize that the entropy that we have found is an extensive value. If you double the amount of particle, volume, and energy, the entropy also doubles. You should take a moment and look at the final equation to understand why this is true. In this final chapter, we will link our findings to thermodynamics. First, we will see what is the cause of the second law of thermodynamics, which states that the entropy of an isolated system must always increase or stay the same. Then we will check if the entropy that we have found is indeed the thermodynamics entropy defined by Clausius. After that, we will see why heat flows from high to low temperature, and we will really understand what temperature means. To conclude the video, we will see the implications of the second law to the full universe. To get a first look at the second law of thermodynamics, we will go back to the harmonic oscillator problem. The amount of microstates was given by the binomial coefficient, and for the following system on the left, we can show that there are roughly 10 to the power 28 microstates. If we denote omega c, the amount of microstates where all the quanta are clustered on one of the oscillators, we can compute the probability that the system is going to be in one of these microstates. Because there are 49 different oscillators, there are 49 different microstates where all the quanta are on one of the oscillators. The probability is therefore 49 over the total amount of microstates, which roughly gives 10 to the power minus 27, which is an extremely low probability. If we consider that the system is changing microstate at a given interval, we can try to compute how many steps we will need to wait to observe at least one of these microstates with a given probability. This probability we are interested in is given by 1 minus the complementary event, which is that we do not observe this macrostate. The power n here is the amount of trials. We can therefore isolate n, which yields the following result. If we set the probability of observation to 50%, the result we get is 10 to the power 27. If we consider that the system randomly changes state every attosecond, which is 10 to the power minus 18 seconds, and which is an extremely generous approximation, we would then have to wait for 31 years. This gigantic time we have to wait is only for 49 oscillators and 49 quanta. Now imagine if we had a real crystal, which is composed of many more oscillators and quantas. This is why we said that the energy has a tendency to spread out. If we start in a known state of low entropy, where all the energy is given to one of the oscillators, then the system will not be able to remain in that macrostate where the energy is concentrated, because there are so many more microstates where the energy is spread out. And so the macrostate of equilibrium is also going to be one where the energy is spread out. Intuitively from classical thermodynamics, this is what we expect. The crystal has a homogeneous temperature. Let's see a second example where we have two crystals side by side with the same amount of oscillators. However, they don't have the same amount of quanta of energy. At first, there's a green separation that doesn't allow them to exchange their quanta of energy. However, this separation is then removed, which allows them to exchange quantas, and we just pick random microstates. As we see, the amount of quanta of energy on each side seems to even out. Yes, there are some fluctuations, but it's nowhere near as bad as the initial state. We can represent the amount of microstates for each configuration, or a given amount of quanta of energy on the left crystal. The total amount of microstates of the full system is given by the integral of this curve. We see that the configuration that has the maximal amount of microstates is the one for which there is 29 quanta on the left and therefore 29 quanta on the right, which are the states where the energy is evenly distributed between the two crystals. If we normalized this curve, it would act as a probability mass function, giving us the probability to find a system in one of the states. We can therefore define a high probability region, which represent the states that would actually be observable with a high enough probability. Here we have a wide normal distribution, because as we noted in the previous example, we had some fluctuations in the amount of quanta on each side when picking a state randomly. But let's see what happens when we increase the size of the system with 10,000 oscillators and quanta of energy. The normal distribution becomes much narrower relative to the total amount of quanta of energy. The observable region becomes much thinner, which means that the overall fluctuations are much lower. If we extrapolated this curve to the thermodynamics limit, which is when the amount of particle is infinite, we would get a direct delta function in the middle, which means that the only observable state would be the one where both crystals have the exact same energy. Using our newly gained knowledge, we will compute the change of missing information for the expansion of a gas and understand why a gas will not spontaneously collapse in the corner of a room, which thankfully allows us to breathe. A gas is first trapped in a box of volume Vi. We then remove the separation without adding energy to the system and let the gas expand in a box of total volume Vf. As we have seen from the classical treatment in chapter 2, the amount of microstates is directly proportional to V power n being the amount of particles. Boltzmann's entropy is therefore proportional to nkb ln V, which you can check back from the Sackur-Tetrode equation in the previous chapter. Because log A minus log B is equal to log A over B, the difference in entropy between the final and initial state is given by nkb ln Vf over Vi. We can also compute the missing information in log base 2. For the experiment shown at the bottom of the screen, the volume available doubled. We therefore end up with n log 2, which is just n. In statistical mechanics, n is usually 10 to the power 23 or even more, so as we can see, our missing information for this has increased tremendously, especially when you compare it to the coin problem we had in chapter 1. The probability that we find the system in a microstate where the gas is collapsed on the left half of the box like originally is given by the initial amount of microstates before we remove the separation, divided by the total amount of microstates in the final state. We get 1 over 2 power n, which if we replace by 10 to the power 23, gives us an extremely small number. By following the same logic as the previous problem, we can try to compute how long it would take to observe a collapse with 50% chance. The edge of the universe is 4 times 10 to the power 35 attoseconds, and the time we would need to wait to observe a collapse spontaneously with only a 50% probability is approximately 10 to the power 30 sextillion times the edge of the universe. Here is a second example of the second law of thermodynamics. This law is only true in the statistical sense, but as we have seen here, to see a major decrease of entropy, the time it would take is so long that it never happens. We can also understand the second law graphically by using the phase space. In blue is the hypersurface in which the system evolves. Keep in mind that this should be a 6n dimensional object. As long as the gas is confined on the left side, the system is forced to stay in a narrow region of the phase space. But as we remove this constraint, the system is now allowed to explore more possibilities. And most of the microstates, in light blue, are ones where the gas is homogeneously distributed in the box. The system could eventually end up in one of these darker blue spots with a lower entropy, but this is extremely unlikely. For the video here, these darker spots are purposely made bigger, otherwise we would not see them. The system remains in its most probable macrostate for virtually ever. As I said previously, we will now check if the entropy we have computed is the same as the thermodynamics entropy defined by Clausius. Clausius initially showed that a small variation of entropy was equal to a small variation of heat the system either receives or gives up, divided by its temperature. In case the system doesn't do any mechanical work, this small variation of heat is directly equal to the small variation of energy. So we want to see if Boltzmann's entropy, given by kb ln omega, is indeed the entropy defined by Clausius. Let's suppose that we have a microcanonical ensemble composed of two subsystems, which we label 1 and 2. These two subsystems can exchange energy in the form of heat. If we wait for equilibrium, their temperature is going to be the same, which, if we use Clausius relation, is going to give us this constraint on entropy. The total energy of the system is fixed, but E1 and E2 are not fixed, they can vary through the exchange of heat. If we consider a specific configuration, where the system 1 has energy E1 and the system 2 has energy E2, the total amount of microstates for this specific configuration of energy is just the product of the microstates for each system. But keep in mind what we have seen previously. At equilibrium, the macrostate is the one that is the more likely. We therefore need to find which energy split between the two systems has the most amount of microstates. We can therefore treat E1 and E2 as variables, with the only constraint that E1 plus E2 is constant, and see where the gradient cancels out. This gives us the following equation. We can rearrange it by dividing by omega 1 omega 2, and here we recognize the derivative of log omega by the energy. We therefore have identified that entropy, defined by Clausius, is indeed the logarithm of the microstates. The Boltzmann constant just bridges the gap between our energy and temperature unit system. It would be totally possible to redefine temperature as being an energy kBT, so that entropy doesn't have any unit. Something that can be puzzling though is why do we use the log of the total amount of microstates rather than the total amount of microstates directly? First, we have to remember that we made our calculation in the microcanonical ensemble, where every microstate has the same probability. But in other ensembles, the microstates don't necessarily have the same probability. And this is why the total expression of entropy becomes important, because it doesn't simplify. The second thing is that entropy is an extensive quantity. This means that if we separate our subsystems and they become completely independent, the total entropy is the sum of the entropy of each subsystem. But the total amount of microstates is the product of the microstates of each subsystem. This is why we need the logarithm. We can also make the link with information theory. Remember that in chapter 1, we have seen that if C is the joint of two independent events A and B, then the information content of C is equal to the information content of A plus the information content of B. If you look at the above equation, the logarithm of omega 1 is just the information content we would get if we were able to retrieve in which state the system 1 is. And the same thing goes for system 2. Because these two systems are completely separate, if we were magically able to find in which microstate the system 1 is, it would give us no information on system 2. To conclude this chapter, I would like to change the way you understand temperature. Temperature is defined as the derivative of energy with respect to entropy. For the crystal made of harmonic oscillators, after computing entropy, we can express the energy in terms of entropy. The curve will look like this, and the temperature is given by the tangent line displayed in orange. At low energies, the tangent line is pretty flat. We get cold crystals. But at higher energies, the tangent line looks more vertical. We have hot crystals. We want to understand why energy, in the form of heat, flows from high to low temperature. If we remove a lot of energy on the hot crystal, we see that the entropy only decreases by a little. Now, if we give this energy from the hot crystal to the cold crystal, we realize that the entropy increases by a lot. So the total entropy of the system has increased, which also means that the total amount of available microstates of the full system has increased. But there's a subtlety that needs to be noticed. The fact that the entropy of the hot crystal has decreased less doesn't mean that its total available microstates have decreased less. This is because the total amount of microstates is a product and not a sum. On this graph, we plot the product of the microstates. Omega 1 and omega 2 are respectively the available microstates for the hot and cold crystals. Out of equilibrium, the hot crystal has more microstates than the cold crystal. We can locate where we are on the product surface. The microstates are displayed in an arbitrary normalized unit. If both crystals are identical, then they will reach a point on the surface where they both have the same amount of microstates. The transformation may look like this, and as we can see, the hot crystal loses more available microstates than the cold one gains. But even then, the total amount of microstates still increases because it is just the product of each subsystems. This is a prime example of why it's more convenient to look at the entropy variations rather than the microstates directly. Because entropy transforms a nonlinear relation into a linear one, where we can simply use a sum. It's hard to associate an entropy to the full universe, especially since it is not in equilibrium, but let's extrapolate our findings even if it's not super rigorous. If we treat the universe as an isolated system, then its entropy must increase. The universe started with a homogeneous and very dense plasma. While this macrostate looks like it has high entropy, it is actually extremely unlikely for a dense plasma to be very homogeneous, because gravity pulls everything together. The explanation why the universe started with low entropy is an open question in cosmology. Then, as the entropy of the universe increases, stars and galaxies formed. This is the macrostate of the universe we live in. Then, if we consider a heat-death scenario of the universe, the entropy will keep increasing and everything will end up in a black hole. Then, if black holes can evaporate through Hawking's radiations, we will end up with a low-density, homogeneous universe. In contrast to the initial state, the reason this homogeneous state has high entropy is because it has very low density, so gravity plays a minor role. Our universe will be in its most likely state.